Hello and welcome to another class of ATMO 620. Today we are still talking about radiation, and in particular we will talk about a very important topic that is scattering. Now, we may have mentioned this earlier on in the first lectures, but essentially, as we all know, from experience, common sense, light tends to move on a straight path. But there can be processes and phenomena that make light deviate from its path. Okay? The ensemble of these phenomena is what we call scattering. Okay? There can be a single scattering process, meaning that you have a light beam that is traveling, interacts with some medium of some sort, and the medium deviates the light path. Or there can be many scattering events. So you interact many times with different media. I know it's not very clear, but these dots are like, these could be atoms and whatnot. So in one case we talk about single scattering, the other case we talk about multiple scattering. And we generally would distinguish between different limits when talking about scattering. We talk about Rayleigh scattering when there is an incident light that has a certain wavelength, and the object on which that interacts with light is a lot smaller than the wavelength of the light. We talk about Mie scattering when the object with which light interacts has a similar size to the wavelength. Okay, and we talk about, in general, we talk about geometric optics when the wavelength of the sunbeam is a lot smaller than the object that interacts with light. Okay, let's start with the simplest case of all, which is Rayleigh scattering. And in particular, let's talk about a very simple setting on which we can study the scattering. At the end of the day, we want to use this very simple setting to learn something about the properties of the wave that is scattered. And in a way, you could enunciate the problem like this, that you have some light beam that is coming in with a certain angle, and the light beam is an electromagnetic field. Okay, so here I'm just representing the electric field by just for simplicity. And this electric field interacts with some object, and as a result, the electric field is modified. And so we want to know, given a certain initial electric field, what is the final electric field going to look like? Okay, we are going to assume that the electric field has some generic direction that we can always decompose in a vertical direction UR and a horizontal direction UL. Okay, like this. And in principle, the electromagnetic, the sunbeam, okay, that is associated with this electromagnetic field is then scattered away with some angle, okay? And the scattering angle, we'll call it theta. And theta is the angle between the previous direction of the sunlight and the new direction of the sunlight, okay? And in addition, we will add two new angles, okay? Gamma 1 is the angle between the direction of this light beam, okay, compared to the vertical, and gamma 2 is the angle between the direction of the outgoing wave, if you will, and the perpendicular direction to the direction of motion. Okay. For simplicity, we will assume that this yellow, outgoing wave is in the same plane as EOL, or if you will, we rotate the coordinates in such a way that this is exactly that the horizontal, that this light this light beam lies precisely on the horizontal, and based on that, we decompose the incoming radiation electromagnetic field into two different components, vertical and horizontal. And furthermore, we will assume that this object has some kind of an electric dipole that we will denote as P. And this electric dipole will also be decomposed in a vertical and a horizontal component. Okay. Now, we will assume that originally the electric dipole, we'll call it P0. And as we know, the electric dipole is proportional to the electric field by some proportionality constant alpha, okay, which is important. And we will, essentially, we are applying a field to this dipole that is oscillating, right? Because, I mean, light is a wave, okay? So the electromagnetic field is a wave, and so for a point such as this one, the electric field is oscillating up and down, okay, if you're not moving. The oscillating field is also going to make, obviously, the electric dipole oscillate, and this is a classical result from classical electrodynamics, that the scattered electric field is given by this formula here, okay? E is 1 over c squared, where c squared is the speed of light. 1 over r, this is the distance from the object. This is the second derivative of the electric dipole. And sine of gamma is the angle with which the light kind of is scattered, okay? So this is still kind of generic. How can we make this a bit more specific to the situation that we're examining? Well, let's assume that the dipole is indeed oscillating, okay, and it's oscillating with with some frequency and with some form like this. Now, pay attention. If we covered this at the beginning of the class, I think, but just as a refresher, if I asked you to write down a wave, you'd probably write something like this: cosine of how can you write this? Well, I can use the same notation here: kr minus ct. Okay, or if you will, well, better way, a more natural way to write it, I guess, would be cosine of kr minus omega t, okay, where omega is the angular frequency and k is the wave number, okay, and okay, so how do we go from a cosine? Obviously this, because the wave number is nothing else but omega over c, this you can also rewrite as cosine of k that multiplies r minus ct. Okay. Excellent. Okay. So how do we go from a cosine to this complex exponential? Well, you should remember these important formulae that I think are due originally to Euler, that e to the ix, okay, equals to cosine of x plus I sine of x, okay. The important part here is that the real part of the complex exponential, okay, so the real part of e to the ix, I mean, this is quite obvious. The real part is literally the part that doesn't have the imaginary unit. This is cosine of x. The imaginary part of e to the ix, you guessed it, it's sine of x. Thus, if you don't want to use a cosine of x, you can just switch to e to the ix, and then whenever you want to get your final results, you can just take the real part and you're done. Easy peasy. Why would you want to do that? Well, because dealing with exponentials, it's always a lot easier than dealing with sines and cosines, and and generally with trigonometric functions. Okay, well, if you do that, then remember that we're assuming p therefore is looks like this. Remember that we had a second derivative of p with respect to time, and so now you have an exponential. So this would be the second derivative would have certainly p0. It would still have the exponential, okay, I to the minus kr minus ct times now the second derivative of the exponential with respect to time. And this would give you minus ikc, right, squared. So this is p0. Minus the minus squared simply becomes a plus. I squared gives you a minus 1. Okay. K squared, c squared. That's just what it is, times p0 e to the minus I kr minus ct. Okay. So put everything together. You plug it back in. And remember the formula, it was 1 over c squared dp, let me remind myself, 1 over r, okay, sine of gamma. Okay, so you put everything together and you get to something like this. So this is the electric field that comes out, okay? This is excellent, but then what do we do with the electric field? The electric field is something that may be hard to measure, so maybe we want to deal with something a bit easier, which is the intensity of the scattered radiation. Okay, so then let's compute this intensity. First of all, let's, because there are all these angles involved, it will be good practice here to decompose the problem into the two main directions that we considered, right? Remember the geometric construction of what we had. So we had a vertical direction and a horizontal direction, both of which are perpendicular to the propagation. Okay, this. So we will assume, as we said, that the angle between the outgoing wave and the incoming wave is theta. And so the angle between the outgoing wave and this horizontal direction is gamma 2. And the angle between the outgoing wave and the vertical direction is gamma 1. By construction, we're assuming that this guy here is on the horizontal plane, okay? And so gamma 1 is actually pi over 2, right? It's 90 degrees. And gamma 2 is related to theta, is related to theta because this is pi 2 minus theta, right? It's pi 2 minus theta, okay? And so the horizontal component, the vertical component has the gamma r, which is what I'd call gamma 1. My apologies for the confusion. Sine of pi over 2 is just 1, so this goes like this. Sine of gamma 2, I remind everyone that sine of pi over 2 minus alpha equals cosine of alpha, okay? And so sine of gamma 2 is simply cosine of theta, where theta is the scattering angle. The intensity of the radiation that is coming out is proportional to the square of the modulus, okay? And this is where it is advantageous to use complex exponentials, because this guy here is e, too many bars, excuse me, can't even write e anymore, e times its complex conjugate, okay? So now it doesn't matter, this is by definition a real element, okay? And so having gone through the cosine way and then taking the real part, or just, having gone the cosine way or the complex exponential way with then taking the real part, doesn't make any difference here. So you do these things. So you multiply these guys by their complex conjugate. The complex conjugate of something like this, for example, would look like minus E0R e to the plus IKR minus CT. Remember, complex conjugate simply means substitute I with minus I. R k squared alpha. So taking the complex conjugate has the effect of getting rid of these complex exponential and squaring everything. Okay? And if you do that, you get to something like this, okay? Where I0R is the incoming, I0R is E0R squared, and I0L is E0L squared, okay? And so you get to something like this. We could go even further and say, well, let's just assume that I0R and I0L are both equal, okay? So radiation is not polarized, and they're equal to some constant I0, in which case this is the formula that you end up having, okay? One important thing that I want to draw your attention to is this. This comes from the wave number from kappa, and you had a kappa to the fourth power, and as a result, the intensity of the scattered radiation goes like 1 over lambda to the fourth, which means, and we'll talk about this in a minute, that shorter wavelengths will be scattered more. So higher frequencies will be scattered more than low frequency waves. Okay, and also importantly, there is a dependency on the scattering angle. Okay, and so for example, when theta equals to 0, then cosine of, meaning that we're considering the intensity in the forward direction. Okay, the light is coming like this. Theta 0 means in this direction. There is a relative maximum, of course, okay, because this equals to 1, and so 1 plus cosine squared theta over 2 is 1. If theta is pi over 2, then this is 0, okay, and so this factor is 1 over half, and so there is a reduction in the intensity at perpendicular angles. If pi equals minus theta, so the radiation that is backscattered, there's another relative maximum, and pi is 3/2 theta, there's again a minimum, okay? So the intensity is maximum for the forward scattering, back scattering, and minimum at perpendicular angles, okay? This parameter here is a bit complicated, and we don't need to know everything about this. Just kind of remember, we'll see something a bit more complicated in the next few slides. Kind of remember what this looks like. And yeah, it depends on essentially the refraction index of the medium, okay? And the refraction index says something about how hard it is for light to propagate inside of a particular medium. There are other ways to write this, and one way is to write it like this, where we define a function p theta, okay, like this, and we also define sigma as the sort of a cross section, if you will, and this would be alpha squared 128 pi to the 5th power over lambda to the 4th, if I've done everything correctly. Okay. There is no new information in this way of rewriting things, but it's just important because then we'll see other limits in which these guys are written in different ways, okay? This you could really think of as a cross-section. Remember, when we talked about cross-section, we said, well, the cross-section is the area of the target that you see as you're approaching it, right? And so when you had a sphere, the cross-section was this circle, okay, of radius r that you saw approaching it. And in a way, this is, even if it's an unmaterial thing, because we're assuming that the object is really, really small, maybe just a point, but there is a sphere of influence around this point, right? And if you fall within this sphere of influence, as a ray, if a ray of light falls within this sphere of influence, then it's scattered away with some angle. Okay, if you are outside the sphere of influence, then it's like there's nothing at all. And this sphere of influence, the interesting thing is that it depends on the light that is hitting the target. And so very, very energetic light will have, this is very small, and so sigma will be very large. Okay, and so for light that is super energetic, sigma will be really, really large, meaning that it's a lot easier. Light has, sort of more energetic light has more chances to interact with this particle here. When lambda is really small, it's really dark, like far infrared or whatever, then the sigma is going to be really, really small, and so it's a lot harder or a lot more unlikely for an interaction to happen. Okay. And this is just shows as a function of the solid angle. It just shows what the intensity of radiation looks like for incident radiation that is unpolarized in our case, which is what we had considered, but we could also have considered cases that were vertically or horizontally polarized. And in one case, I0R or I0L would have been 0. Okay, but just think about this for unpolarized radiation. Okay, but so let me remind you all that the intensity of the radiation goes like 1 over lambda to the 4th power. Okay. Remember that blue light has a wavelength of about 425 nanometers, whereas red light, 650 nanometers. This difference matters a lot given that you have a power to the 4th here. And so blue light scatters almost 6 times more than red light. And so, when you have an atmosphere, white light is coming in from the sun, all the different colors are going to interact with the molecules of the atmosphere differently. Red light is just going to go straight down, yellow light is just going to go straight down, green light, it's starting to bounce around. But blue light, on the other hand, the moment that it enters the atmosphere, it starts hitting molecules everywhere. And so blue light, as a result, starts to travel everywhere in the atmosphere. And that is why we perceive the sky as blue. Actually, some of you would have noticed that there is, if you look at the rainbow, there is a color that is beyond blue that we can perceive, and that is violet. So what's up with that? Why isn't the sky violet? Which, in my opinion, it would look even better. But why isn't the sky violet? Well, the answer is very simple. If you remember the sort of the Planck's spectrum, okay, this was the irradiance, and let's say this is wavelength. Blue is here, we could say, and violet is here. So violet should scatter more, but fortunately or unfortunately, violet has a lot smaller intensity, has a much smaller intensity than blue, and therefore there is less to scatter around to begin with, and that's why we don't see the sky as violet. Also, relatedly, why does the sky turn red at sunset? Well, I think we can all agree that the Earth is spherical, so this is the atmosphere. If the atmosphere has a certain thickness, let's say, 100 kilometers more or less, light is coming in, red light doesn't care, blue light is scattered everywhere. But now, obviously I'm exaggerating. Red light is also scattered around, only not as much as blue light. But when light is coming in with an angle, okay, so it's coming in with an angle because the sun is setting, the path that light has to travel to get to your eyes is a lot larger than what it had to do at noon. And so blue light will certainly start to scatter, in every place. But the result of that is the blue light kind of runs out really, really quickly. And so the light that is left at the end of the path, and that gets all the way down to the lower part of the atmosphere, is reddish and yellow light. And this still scatters a little bit, okay? Even, not as much as violet, but the intensity of blue is too low in this case to make any difference. And so that's why we see the sky as red. Also, one thing I wanted to say is that, interestingly, real molecules are not really homogeneous and isotropic, which is what we had kind of assumed. And as a result of that, the light that is scattered because of Rayleigh scattering can show some polarization. In particular, light at 90 degrees is completely polarized, which is an interesting fact. It is also one of the reasons why you have things like polarized sunglasses, for example. That's why they work, because they block out, they have the opposite polarization. They let through the light that has the opposite polarization of what is scattered away, and so the light that is polarized doesn't go through your glasses, and so you don't actually see those photons. Okay, so much for Rayleigh scattering, which happens, as we said, when the object on which you're scattering is a lot smaller than the wavelength of the light that is hitting the target. What happens when you're not in this limit, when the object is actually of the same size? Whenever you have a situation like this, when you have well, this is a tricky limit, because when things are either really, really small or really, really big, chances are you can always make some kind of simplification. So, if you have something like 1 over 1 plus x, just to give you a sense of this. If x is really, really small, okay, then you can simplify this as 1 minus x, okay? If x is really, really big, then you can define y equals 1 over x, okay? And this becomes 1 over 1 plus 1 over y, which is y over y plus 1. Okay, where now y is really, really small, and so you can still say, well, this is y times 1 minus y. You can always make some kind of simplifications like that, and higher orders will be kind of cut down, okay? But when things are of a similar magnitude, so when x is of the order 1, is of order 1, then there's no good simplification that you can make, and you're kind of stuck with a complicated formula. For scattering, when you are scattering against an object that has a similar size as the wavelength of the incident light, then you're kind of in trouble, because some of the simplifications you can use are not valid. In this case, we talk about knee scattering, and you can show with very complicated calculations that the intensity of the scattered radiation can still be written with this simple formula, but now sigma is a lot more complicated than before. Sigma, in particular, is a very, very complicated polynomial that depends on a lot of different factors. First of all, A is the size of the object that we're scattering against. Lambda is the wavelength of the light, and x is this kind of dimensionless parameter of order 1, okay? Then you can show that a normalized sigma will look like something like this, okay? And so this is interesting now because you have to keep all these terms. And so you don't have to memorize any of this. But the bottom line is that, yeah, things become really, really complicated really quickly. And interestingly, you can show that. I'll not do it, but you can show, and you can kind of see why it works, that when if you were in the limit where A now suddenly becomes a lot smaller than lambda, then X become really, really small, and all these additional terms can be dropped. And you're left with the leading term, which is C1 X to the 4, and X to the 4, guess what? It has, it looks something like 1 over lambda to the 4th. The A's simplify, yada yada yada. Well, at the end of the day, what you end up with is the Rayleigh scattering. Okay, when you go in the limit where of validity of Rayleigh scattering, you find the formula of Rayleigh scattering, which is good, and it's also what you would have expected. So excellent. The other thing I wanted to say is that obviously with Rayleigh scattering, if you remember, let's say that there is incident light that is coming in with this direction, then the scattered light has a maximum for forward scattering, a maximum for back scattering, and a minimum for sort of lateral scattering. For me scattering, it's kind of different, and it's only for forward scattering that it really does have a maximum, okay? Okay, the thing I also wanted to say is that when you have large sort of aerosol and cloud particles, these are now of the kind of the same size as the wavelength. You know, now you have 0.1 micrometers, which is of the order of 100 nanometers, which is now suddenly comparable to 400 or 500 nanometers, which is the wavelength of visible light. So in this case, interestingly, intensity is more dependent on the size of the particle than the wavelength of the incident radiation. And as a consequence, light is scattered, light of all frequencies is scattered kind of similarly by aerosol particles, okay? What that means is that, you know, if you have a sunbeam that hits a cloud, the cloud will scatter this light beam, but it will scatter it in such a way that it will scatter white light. And that's why clouds appear white. Sky is blue because molecules are small and Rayleigh scattering, but clouds are white because cloud particles are big and me scattering. Okay, so just keep in mind these things. Finally, last thing, we will not deal too much with this, but when the size of the object against which you're hitting is really, really big, then we are in the realm of what we call geometric optics. And in this case, scattering phenomena are what we call diffraction patterns. And there's a way to predict, you know, exactly the shape of these diffraction patterns. We will not care too much, but just keep in mind that that's what it is. Okay, I want to conclude this lecture with a simple model of scattering that is discussed in the textbook, okay? This one is kind of more related to the stuff that we were discussing the other times, and in particular, it's a simple model that allows us to derive some simple functions to compute the incoming and outgoing spectral irradiance on Earth, if you will, okay? This simple model, first of all, assumes plane parallel atmosphere, meaning the Earth is flat. The atmosphere is also, so the Earth is flat. The atmosphere is also flat, and we assume a two-stream approximation, meaning light is coming in perpendicular to the atmosphere and to the surface of the Earth, and there's outgoing radiation, again, perpendicular, yada, yada, yada. We'll have to make the diffuse approximation here and also modify, when we'll talk about the optical path, we'll have to modify this with the factor that we had discussed before, okay? Now, in this case, if we just focus on the downward pointing spectral irradiance, spectral radiance. Radiance or irradiance? Can't make up my mind. Spectral irradiance, okay, because we're integrating over everything and we're using the effective optical path. My apologies for the confusion. This will simply be made of an absorption term. Okay, some of this will be absorbed along the way. Okay, this is expressed here. There'll be a backscattered component, so some photons will be just scattered back. Obviously, in the real atmosphere, photons are scattered pretty much everywhere, but here we're thinking that radiation only either goes down or goes back up again. Okay, so some will just be backscattered. And we call the fraction, we say that F is the fraction of radiation that is scattered forward, and so 1 minus F is the one that is scattered back. Okay. Also, some radiation is coming out of the surface of the Earth, but some of this will also be scattered back. Okay, and so we'll also have to consider this. Okay, this will be contributing. It's a bit like a source function, if you will. Right? Very good. So we can arrange the equation that we defined earlier, and we introduce our good friend again, the extinction coefficient, which was just the sum of the absorption and the scattering coefficient. So remember here we had S times 1, S rho 1 minus F, and so we can just take S rho times 1 times F down. We can pack this together with A rho F down, and we can make a K nu rho A F down, which is exactly this. K nu rho A F down, plus this is the reminder of that backscattered component, and this remains what it is. Now, K nu rho A does many terms, and so we just want to divide by the optical path, the effective optical path, and be done with it. And to simplify things even further, we define S nu over K nu as the albedo, and we call this omega nu. Okay, let's just drop the nu for simplicity, and the above equation can just be written like this. Okay, something simple holds for upward irradiance. Okay, and if you do the calculation, it's essentially the same, right? Because some of the upward irradiance will be absorbed, some will be backscattered, and some will be contributed by the downward irradiance that is backscattered and is now going upward again. Okay, so this contributes to this. This can be solved. This is a very simple system of two differential equations in two unknowns, and this can be solved very simply. We can impose two boundary conditions, one at the top of the atmosphere, and the top of the atmosphere is at optical path 0, because the atmosphere hasn't even started there. And in that case, we can say that the incoming radiation is some irradiance, spectral irradiance F incoming. The outgoing is some F reflected. And then at the surface, this will be some optical path, chi star 1, okay? There'll be no upward going radiation at the surface, because we're assuming that the surface of the planet does not emit any radiation in the spectrum that we're considering. And the downward that is coming down at the surface, we just call this F transmitted. Now, you can do all the calculations, and if you do, you will find that F down and F up can be written as simple functions of chi star, of the optical path, and particularly as linear functions of chi r. They'll depend on the incoming radiation, that kind of makes sense, and also on these coefficients r and t, where these are, t is the fraction of the irradiance for transmitted radiation to the incoming radiation, and r will be the ratio of the reflected irradiance, spectral irradiance, to the incoming spectral irradiance. Obviously, by conservation of energy, what is incoming is also equal to what is transmitted, so what managed to go through plus what is reflected. Okay, so if you divide everything by F inc, you'll get that T plus R equals to 1. Okay. In more complicated cases, obviously, you'll also have, the irradiation is incoming, but there's also some absorption from the atmosphere. Okay, and you'll have to take that into account. And so, in general, r plus t is not equal to 1, but is smaller than 1. But yeah, this was just a simple model that shows you how to compute the incoming and the outgoing radiation as functions of the optical path, particularly as linear functions of the optical path. Okay, so this concludes what I had to say for this class on scattering. I hope it was clear. I hope you guys enjoyed it. And if you have any questions, please feel free to get in touch. Otherwise, I will see you guys for our next class. Thank you so much for listening.